All right, so when you're solving physics problems at first, before you really get good at it, a helpful way to figure out if you're using the correct equation or not is dimensional analysis, right? So basically what we're going to do is analyze the units given by a formula, and they should match the unit you're looking for. So let me show you an example of what I mean. Let's say I want to find the volume of a sphere, right? And I took geometry, right? And I remember there's two formulas that have something to do with like circles and spheres, right? So I remember there's pi r squared, right? I remember that from geometry. And then there's also 4/3 pi r cubed, right? So I don't know which of these is the right formula for volume of a sphere, right? But I remember them. And so the question is, I want to figure out which one is right. Okay, so instead of like going and looking it up, because you're not always going to have access to stuff like that, right? An easy way to do it really quick is to do dimensional analysis, right? So I know volume is measured in cubic meters, right? So that's a meter times a meter times a meter. That's the base unit. So let's go through and look at these units and figure out what the units of these come out to, and do they come out to meters cubed, right? So let's start with this one. So pi is a dimensionless unit, right? It's a constant. So this doesn't have any units, right? That's a constant. And r squared, r is measured in meters, right? So that's meters squared. So when I look at this one, a constant times meters squared, that means my units here are going to be meters squared. Volume's in meters cubed, right? So I know that's not correct. Okay, let's look at the other one. So this one, 4/3 and pi, both of these are constants, right? 4/3 is a constant, pi is a constant. Okay. R cubed, that's meters cubed, right? Because r is measured in meters. R is a radius of a circle, right? That's r. So this is meters cubed. So this one is measured in meters cubed. And wow, I know volume is meters cubed. So that means meters cubed. This has to be my formula for volume of a sphere. Okay, so let's look at another one involving projectile motion. A lot of times when you do projectiles, like lazy teachers will just give you the range equation instead of like teaching you about projectiles. So like imagine you shoot something, you throw a football or whatever, right? You throw something in the air and it makes a parabola. The range is the distance that it travels horizontally, right? And so if you're just given the range equation, the range is initial velocity squared sine 2 theta over g, right? So let's check and see if this range equation works out. So I know range should be measured in meters, right? Because I'm measuring a distance. So let's look at what the units of all these things are. So initial velocity is meters per second, right? So that's going to be there. This whole thing, sine 2 theta, this is all a constant. There's no units for theta, right? The radians are degrees, but radians, theta's unitless, right? I'll show you that in a second. And then for g, that's the acceleration due to gravity or the gravitational field. That's meters per second squared. Okay, so now let's look at this. All of this is a constant, right? So that's not going to be there. Meters over seconds squared, that's meters over seconds quantity squared. And then I have g in the denominator, so g is meters per second squared, right? So there's my units. So let's simplify this and see if it works out to meters. So I can do some algebra, right, and rewrite this as this, right? Because I did algebra and I distributed that square in, right? And then I multiplied by the reciprocal, so I moved second squared up and moved meters down, right, to get it both in the same thing like this, right? Algebra. Okay, so now we can simplify. The square cancels out one of the meters. Second squared, second squared. Wow, it works, right? So the range equation, yes, you can use the range equation, but when we do projectiles, we'll actually, learn about it instead of just giving you a range equation. Okay, so we just talked about radians and why radians are dimensionless. So let's look at that really quick. So if you remember a radian, what the definition of a radian is, right? This is the radius of a circle. This is the arc length s, and this is theta, right? Radians, the angle in radians, is equal to the arc length divided by the radius, right? This is the definition of measuring things in radians. So arc length is going to be a unit of distance, right? So whatever, call it meters or centimeters, whatever. This is a unit of distance, right? So s is in meters. R is also a unit of distance, so that'll also be measured in meters. And look at that, it cancels out. This is why radians, right, when you look at radians, they are dimensionless. There's no dimension to them. Okay, so let's do a little more complicated one. Let's use dimensional analysis to figure out the units for a constant. So this is Coulomb's law. Coulomb's law tells you the electrical force between two charges, right? Like a positive and a negative charge, like how much they attract each other, right? So I want to figure out the units for K, okay? So let's look at the units for all these other things. So I want to find units for K, which is called Coulomb's constant. Okay, so the units for all these. So force is measured in newtons, right? Q1 and Q2, these are measures of charge, right? And charge, like I don't expect you to know this because this is only physics 1, but charge is measured in coulombs. Coulombs is a base unit. There's no apostrophe there. I'm dumb. And then R is a measurement of distance, right? So let's say the base unit's going to be meters, right? So here's my units. And a newton, right? A newton I can rewrite in base units. Remember, force is mass times acceleration. So a newton is really a kilogram times a meter per second squared. Mass times acceleration. Okay, so now let's look at all this and write it out. So my units over here are kilogram times meters per second squared. That equals the unit I want to know times all these units. Well, Q1 and Q2 are both in coulombs, so that's coulombs times coulombs. R squared is meters squared, right? Because the meters get squared because of that square. And so now if I want this unit, I can just get everything on one side, right? So I'll move this over and I'll move that down. So this unknown here, the units are going to be kilograms times meters squared, right? Because I'm going to multiply by meters squared to move this over. So that's going to be meters cubed over seconds squared times coulomb squared. And that seems crazy. Like, what's that good for? But that's the unit for Coulomb's constant. So I want you to try one on your own. So let's say you're solving a problem, right? And you just write down velocity is acceleration times displacement. Trying to solve some sort of kinematics problem, and you pull this out of your rear end. Let's see if this works, right? So before you go start trying to plug stuff in and solve, see if it works. Okay, so we know velocity is measured in meters per second. And you know acceleration is measured in meters per second squared. And you know displacement is measured in meters. So you pause the video and you tell me, do these units work out? Is this equation correct? Pause it, do what we just did, figure it out. Okay, so let's check this out. So velocity, that's meters per second. Acceleration is meters per second squared. And x is distance, so x is going to be meters. Okay, so let's see if this works. So this is meters per second over here, so this should cancel out. Oh no, I already see there's a problem, because meters times meters is going to give me meters squared over seconds squared. So this equation does not work. Can't use that. Okay, so you can see this is pretty powerful stuff when you're trying to solve problems. If you're ever, stuck trying to decide if an equation is reasonable to use, then this is a really good first step to take.